Hello everyone. This is lecture 51 of Principles of the Electric Circuits. We will review the circuit response from another aspect. Let's have a review first. In lecture 47, we've introduced that the solution of any inhomogeneous linear ODE with constant coefficients can be expressed as a sum of general solution and special solution. In lecture 49, from the viewpoint of system, general solution and special solution can be represented as natural response and forced response respectively. In common first-order circuit, R, L, C are all positive, so time constants is positive. In lecture 50, the solution of any branch variable is written as a steady-state value and natural response. All these methods are more and more close to the expression of circuits. But in this lecture, the solution will have a new classification. It's more suitable for our thinking habits about circuits, and much easier for solving the circuits. In this classification, the whole solution is written as the sum of the zero input response and the zero state response. Our discussion starts from a simple exercise. This circuit is a series connection of a voltage source, a resistor, and a capacitor, whose initial value is U0. By applying three elements method, we know UCT can be written as US plus U0 minus US multiplied e to the power of minus t over tau, in which tau equals RC. We've been familiar with this method in lecture 50. Now we focus on other two circuits. The first one is called the zero-state circuit. Here the state means the energy stored in the energy storage elements in dynamic circuits. Specifically, zero state means UC is 0 or IL is 0. So the zero state circuit for the above circuit is like this. This is also a first order circuit. Similarly, we can use three elements method to solve it. This is the solution. Besides the zero state circuit, the second is a zero input circuit. As we know, the transient process of the dynamic circuits is caused by two key factors. The first is the energy storage elements in the circuit. The second is the switching of the circuit. Basically, the transient process of dynamic circuits is caused by the change of energy in energy storage elements. If the circuit has no inputs, but energy storage element has initial values, it will still have transient process once the switch is turned on at t equals 0. This is also a first-order circuit, which can be solved by the three elements method. This is the solution. The solution of the zero-state circuit is called the zero-state response. The solution of the zero-input circuit is called the zero-input response. You can see that the sum of the zero-state response and the zero-input response is just the response of the whole circuit, which is called the full response. Why so? Let's think about this question from the aspect of the superposition theorem. We just discussed that the transient process of dynamic circuits is caused by the change of energy, which can be provided by external independent sources or internal previously stored energy. So a circuit with external independent sources and internal previously stored energy can be divided into a circuit only with external independent sources and a circuit only with internal previously stored energy. Obviously, ZSR plus ZIR equals FR. This is the expression of a full response, which is the sum of ZSR and ZIR. Now we draw the waveform of two responses. For zero-state response, Because the initial state is zero, the capacitor voltage is charged from 0 to Us. For the zero input response, because all the energy of the circuit is stored in the initial stored energy of the capacitor voltage decays from U0 to 0. Their sum is the full response. You see, in this way, the waveform of the full response is the same as the waveform of the solution from three elements method. You must remember that the full response of a circuit is the sum of the zero state response and the sum of the zero input response. Why so? Firstly, let's have a review. In lecture 46 about capacitors and inductor, we've introduced their differential and integral relationship. Let's have a retrospection here. For a capacitor, the differential relation of the voltage and current is linear, obviously. But the integral relationship of the voltage and the current is nonlinear. There is a constant U0. If U0 is 0 in zero state condition, ut equals 1 over c multiplies the integral of I. So the differential and integral relationship of the voltage and the current are both linear in zero state condition. With the linear differential and integral relationship, we can easily use superposition theorem to analyze and solve the circuit. Similarly, for an inductor, its differential relationship of the voltage and the current is linear, and the integral relationship of voltage and current is linear in zero state condition. With the above knowledge, we've had further discussion on the solution. For this zero state circuit, we know UC equals US multiply 1 minus e to the power minus t over tau, in which tau equals RC. In zero state condition, the relationship between the capacitor voltage and the excitation is linear. Let's verify it. If the excitation is US, the response is this. If the excitation is twice as much as before, the response is obviously twice as much as before. If the excitation is the sum of two excitations, the response obviously is the sum of two responses respectively. Thus, we verified that the relation between the excitation and the response is linear. You should remember that in zero state condition, the relationship between the excitation and the response is linear. With this, we can firstly solve the impulse response of a circuit in the zero state condition, then calculate the convolution integral of the excitation and the impulse response to find the zero state response with any excitation. Maybe you are wondering that after listing ODE related to any branch variable, we suppose the form of special solution based on the right term, substitute it into the equation and compare the coefficient to find the special solution. Why do we need zero input response, zero state response, impulse response, and convolution integrals, which is a complicated process? Don't forget that sometimes excitation can have an explicit expression, so there's no doubt in this condition that we can use the form of a special solution and substitute it into the equation to solve the undetermined coefficient. But sometimes the excitation is just a time domain waveform. Convolution integral is very important in this condition. In this condition, convolution integral is the only solution method. The important concept of the impulse response and the convolution integral is very important but will not be discussed in our course. You can learn them from Signals and Systems or Principles of Automation Control course or the teaching materials of the Principles of Electric Circuits. Okay, this is the end of this lecture.